Hello everybody, and welcome to this lecture on mathematical optimization, presented once again by Onyx. Today we're going to be kind of combining all of the multivariate calculus topics that we have talked about so far and building up into the process of optimization. And optimization is essential for artificial intelligence and neural networks, specifically deep neural networks. This is the process by which we are going to actually make these algorithms learn. It is how we are going to update the parameters so that we are able to minimize a loss function is often what we are trying to do. So we're going to take concepts like the derivatives that we've talked about or the gradients that we've talked about and apply those into this process of optimization today. In this lecture, we're going to focus on example problems in one dimension. In real-world neural networks, you are going to have way more dimensions than one, so this expands quickly. But just so that we can nail down the core concepts, we're going to restrict it to one in this lecture. So let's go ahead and dive in and get started talking about optimization. So the optimization problem is often stated like this. We want to minimize some function f naught of x subject to these particular constraints. So we have two constraints here. F of I of x is less than or equal to 0 and hj of x is equal to 0. These constraints can vary. These are actually the constraints for a convex optimization problem. We'll talk about what a convex optimization problem means in a second. But for now, it's just important to get down some of this terminology. So we have the objective function. That's the f naught here. The objective function is what we are trying to minimize. In machine learning, this would be your loss function. We also have an optimization variable. So these are the variables that go into our objective function. And they're often the parameters that we want to update. So if we had a neural network, the x's here, this is actually going to be a vector of inputs. So we have x0, x1, x2, all the way to x of n. And we want to update those iteratively to minimize the objective function. And here we have a couple constraint functions. Constraint functions can vary. Again, these are the constraint functions for a convex optimization problem. We'll talk about what that means in a second. These constraint functions vary and they can get a lot more complex, so we will only talk about them briefly. So here is the basic problem though. We have a function, we're trying to minimize it. It operates over some variables and we have some constraints as well. Before we dive into this, we should talk about the difference between local and global critical points. So a critical point on a graph here is going to be either a maximum or minimum. It's defined by the fact that the derivative is actually going to be 0. So the slope at a local minimum, maximum, or global maximum or minimum is going to be 0. And so a global minimum we see is the absolute smallest point on the graph here. And similarly, the global maximum is going to be the absolute largest point on this graph. This red line here would represent our objective function. And then we have the local maximums and the local minimums. And they are just going to be the maximum value or minimum value respectively in their local area. So you can see for the local minimum, immediately to the left and immediately to the right, this graph is increasing. We have a concave up graph in that immediate area, and so we have a minimum there. But it's not the absolute smallest, so it's not the global minimum, it's only a local minimum. And local minimums are important because when we're optimizing our algorithms, we can often get stuck in local minimums. So there would actually be other global minimums out there that would minimize or improve our algorithm further, but since we get stuck in these local minimum, the algorithm thinks it's found the very minimal value. So we'll talk about ways of mitigating that as well. So here's convex optimization. We'll mention what this means. And we really have convex optimization if the objective function we are using is convex. And that might be an oversimplification, but it's a very good way to think of it. You also have some requirements on the constraints, but we won't dive into that too much. So a concave function is defined as concave if you can draw a line between any 2 points on f of x, like they've done here in this graph with the red line, and that line lies above all other points of f of x between that graph, or between the 2 points that the line intersects the graph with, then you have a convex function. A similar way to think about this is if the function is concave up or concave upwards, you're going to have a convex optimization problem as well. So on the y-axis and the x-axis here, they've defined the actual convex mathematical proofs, the requirements or the constraints to this problem. The t f of x1 plus 1 minus t f of x2 is going to be greater than the f of x here, the f of tx1 plus 1 minus t of x2. And so that's the mathematical way of saying all points on this red line are going to lie above f of x. So this is a convex function, and when we mention convex optimization going forward versus just optimization, the only real difference is the objective function that we are using. So why is all of this important? Why do we really need to talk about optimization? Well, because in classification, we want to minimize this function. In k-means clustering, we want to minimize this function. And in logistic regression, we want to minimize this function. And the list does not stop here. In almost all machine learning approaches, not just artificial intelligence approaches or neural network approaches, there is some function that we want to minimize or maximize. And that objective function is how we're actually going to have the algorithm learn. This is how machine learning networks learn or improve, is this iterative process of minimizing some objective function. So very important for all areas of machine learning. So let's talk about how we actually do this using calculus. And we're going to start with an example problem. And we're going to show that calculus can be used to find extrema, or the critical points, for an objective function. And all we have to do is use the first and second derivatives. So we have an example problem here. We have y equals x squared plus 3. So very simple equation. And this is going to be our objective function. Let's see if we can minimize it. I'm sure we can. So here's the graph, and immediately we can obviously see where the global minimum is going to be. We know it's a global minimum. There's no other points on the graph. This is concave up. This is actually a convex optimization problem. And we're going to exploit the fact that the derivative at one of these critical points is going to be 0. So we see at the minimum on this graph, if we were to draw a tangent line at that point, it would be completely horizontal, or in other words, the slope would be 0. So we're going to exploit that fact when we take these derivatives, and we're going to be able to solve for the location that occurs at. And this occurs for local minimums, local maximums, global minimums, global maximums. Any critical point that you have, the derivative is going to be 0. So first step first, we got to take the first derivative of f of x. Our y equals x squared plus 3 is our equation. To take the derivative, we have to use the power rule. We're taking the derivative with respect to x here. So y prime, or the derivative of y, is going to be equal to 2x. And that's using the power rule. The x squared, the 2 gets multiplied in the front. 2 minus 1 is 1. So we just have x to the first here. And then the derivative of a constant, 3 in this case, is just going to be 0. So we have our first derivative, and now let's exploit the fact that we just discussed, and that is that the derivative is going to be equal to 0 at the critical point. So this is the important step. We want to set the derivative equal to 0, and then solving for that, this is a fairly simple equation, so we can see just divide the 2 over, x is equal to 0 is where that is going to occur. So x equals 0 is a critical point. If this was a more complex function, we actually wouldn't know if it was a minimum or a maximum yet, or even a local minimum or local maximum. Local versus global, we wouldn't know that either. So what we have to do from here is the second derivative test. That's what it's called, the second derivative test. And all we're going to do is take the derivative again. So we have our first derivative, that's y prime equals 2x. If we take this again, y double prime, or the second derivative, we have x to the first here, so that becomes x to the 0th power, which is, of course, is just 1. So we are left with simply 2. So really easy to do there. And then what this means, if the second derivative is positive, we have a minimum. If the second derivative is negative, it's a maximum. And this actually makes sense. It kind of talks about the second derivative is going to describe the way that the slope is changing. So around x equals 0, the slope is going to be increasing. It's going upwards. So that's why we have a minimum, and that's why the positive corresponds to a minimum. If the slope were to be changing in a negative direction, it was going down, then we would have a maximum because we'd be at the top. We, of course, knew this was going to be a global minimum just by looking at the graph. It's a very simple one-dimensional problem, but it's nice to prove mathematically that that is in fact the case. So here is essentially the steps. It's a first derivative, and then we move on to taking the second derivative where we actually prove that it's going to be a minimum. And remember, if this is a convex function, which it is indeed, we are actually guaranteed that it's going to be a global minimum. So there would be no need to do the second derivative test if we were to prove that it was a convex function in the first case. All right, so in the context of machine learning, let's talk about this. Optimization, you're not just going to take the derivative of some complex neural network and then set it equal to 0. That's not exactly how it's going to work. It's often going to be an iterative process. So we're going to make a guess, we're going to take the gradients, and then we're going to use those gradients and update our parameters and make a slightly better guess the second time. And we're going to do this over and over again until our guesses no longer improve our results. So the gradient, if you remember from the previous lectures, we talked about how the gradient tells us the direction of maximum increase. And so if we actually take the gradient of our objective function, we are going to be able to know the direction of maximum decrease. That is simply going to be the negative gradient. And we can use that to update our parameters. So let's take a look at this example again. Maybe we would start, if this was actual machine learning, we'd start with the guess. Often this is going to be like random noise. So let's just say, we think x equals 3 is the minimum. Pretty bad guess considering the graph's right in front of us, but let's just go with it. So x equals 3 is the minimum. Let's evaluate this. Plugging in x equals 3 into our function, x squared plus 3 gives us 12. If we take the derivative at that particular location at x equals 3, so plugging in 3 to y prime equals 2x is going to give us 6. So this is a positive derivative, which means we have a positive slope. We want to head in the opposite direction because we don't want to be increasing, we want to decrease our objective function. We're trying to minimize this. So we're going to go in the negative gradient direction. Since this is a one-dimensional problem, the gradient is simply the same as the derivative with respect to x. Since there's only one variable, there's no need for partials. It's just the derivative with respect to x. So we're going to head in the other direction. It said positive to the right. We're going to move in the negative direction to the left. So we'll guess something less than x equals 3. Maybe we have a high learning rate and we're going to guess something dramatically left. And we now guess -1 is the minimum. Not a bad guess. -1 is to the left of 3. And we know that the derivative was positive at x equals 3. So heading to the left should give us a smaller value. So we're updating our guess. How much we update our guess by is going to be what is called the learning rate for neural networks. So we calculate the gradients, and then in this case we moved 4 to the left, 4 whole integers. So we had 2/3 of our gradient is how far we moved to the left. In typical neural networks, this value is going to be really small. It goes all the way from, you'll see 0.01 to 1 to the -13th or 14th, very small learning rates. And so if we had, for example, a very small learning rate, our guess wouldn't go all the way to the left to -1. We'd go from x equals 3 to maybe x equals 2.999 or something like that, and take very small steps. But let's say, for the sake of this example, that we went all the way to -1. So we are going to evaluate it again. Our second guess, x equals -1 is the minimum. We evaluate, we have negative 1 squared plus 3, that's going to be equal to 4, so we are indeed getting smaller. And we're going to evaluate the derivative. We now get negative 2. 2 times negative 1 is equal to negative 2, so we know we overshot it a little bit. Since the derivative is negative, we want to move in the opposite direction of that. Opposite of negative 2 is going to be positive 2. That's the positive direction. So we want to increase our guess slightly. Maybe we're going to update our guess and we nail it on the head. X equals 0 is the minimum. So this iterative process is actually how gradient optimization or stochastic gradient descent is going to work in a very simple kind of framework. It's an iterative process. We take the gradient, we minimize our objective function by updating our parameters in the negative gradient direction. And we did this in 2 guesses here, and we also have a very simple equation, but this is going to take thousands and thousands of iterations for neural networks. If you're using deep neural networks, this process has to happen over and over and over again. And again, that's because the learning rate is so small, so we're not changing our guess by much each time, and there is definitely advantages to making the learning rate small. It's not like we can just increase the learning rate because you run into different problems with convergence and that type of thing. All right. So that's optimization. Some of the problems, we mentioned this earlier. What happens if we hit a local minimum? If we're only updating our guess a little bit, we're going from x equals 3 to x equals 2.99, we could get stuck in local minimums very easily. If this is a convex function, again, you're only going to have global minimums, so you'll see different machine learning problems where they restrict the objective function to being a convex function, so that the local minimums don't exist. But again, this is not always the case. So when you're actually training a neural network, you got to take steps to mitigate local minimums if you're not using a convex function. And then again, there's all kinds of different constraints for these problems. So changing the constraints is going to change the context of the optimization problem a little bit. And again, those vary dramatically. So we're not going to address those in too much detail here, since this is just an introduction to the fundamental maths for deep learning and artificial intelligence. All right, so this is actually going to bring us to the end of our lecture here, and this is actually going to bring us to the end of Unit 2 as well. So we are done with multivariate calculus. We've talked about derivatives, integrals, built up from there into gradients in many dimensions, and we talked about some of the operators that are involved with that. And then we have covered here convex optimization and just mathematical optimization in general, which is the process of iteratively improving our parameters to minimize some objective function. In the next unit, we'll cover probability theory, so stay tuned for that. We'll talk about the elements of probability, random variables, variance and expectation, some special distributions as well. And so probability theory is essential on many levels to this type of statistical learning that we are doing in neural networks and artificial intelligence in general. So keep listening. I hope you've enjoyed this Unit 2 and learned a little bit about calculus, and we'll keep moving along. Thank you very much for listening.